Hello everyone, myself Latha N, Assistant Professor of Physics, Government First Grade College, Sullia. Today we will study about the topic filter circuits. Of second BSc, fourth semester. So filters are the electrical networks used to select and pass or reject the desired frequency from a group of frequencies. So filters are the electrical networks used to select and pass or reject a desired frequency from the range of frequencies. So such electronic circuits are called as filter circuits. So there are three types of filters. So first one is low pass filter, high pass filter second one, and the third one is band pass filter. So let's discuss the low pass filter. First, single stage low pass filter. A filter that allows only lower frequency components to pass through them while rejecting the higher frequencies. Such filter is called as low pass filter. A filter which allows only lower frequency components to pass through and rejects higher frequency components. So such filters are called as low pass filters. So in RC low pass filter, we can construct filters in many ways by inductor and resistor, inductor and capacitor likewise. So in this class we will discuss about the RC low pass filter. So the resistor and capacitor is connected as shown in the figure, so that the one end of the resistor is connected to input of the positive of the voltage supply, and the capacitor is connected to other end of input voltage source. So the low pass filter is constructed by connecting a single resistor and a capacitor in series as shown in the figure, and the output must be measured across the voltage and input must be given to the end of the resistor and the end of the capacitor. So if we provide input voltage containing a range of frequencies, the range of frequencies applied to the filter circuit, higher frequencies are bypassed through the capacitor while only lower frequency components are available at the output. So here, when the range of frequencies are given input into the resistor, so the capacitor will bypass the higher frequencies and only lower frequency components will be available at the output. So the frequency response graph or curve is plotted by taking the input voltage across or output voltage along y-axis and input frequency along x-axis. So output voltage versus input frequency. Frequency response curve is plotted taking the output voltage along y-axis and the input frequency along x-axis. So let's observe what happens to the frequency response curve. From the graph, it shows the output voltage is maximum and it is almost constant for lower frequency. So you can observe this. So the output of the capacitor, it shows that the filter output. So for lower frequencies, the output will be maximum and it is constant. For higher frequencies, the output of the filter will goes on decreasing and decreasing, and for higher frequencies it will becomes 0. So for higher frequencies output decreases. So next, cutoff frequency. It is the frequency at which the output voltage is reduced to 1 by root 2 times the maximum output, or it is such a value that the output power is reduced to half of its maximum value. So that frequency, that particular frequency is called as cutoff frequency. It is the frequency at which the output voltage is reduced to 1 by root 2 times the input voltage. That is called as cutoff frequency. In terms of power, we can explain it is such a value that the output power is reduced to half of its maximum value. So we can represent the cutoff power P0 cutoff, which is equal to half of the maximum power. So the expression for power in terms of resistance and voltage is V squared by RL. So in terms of output cutoff voltage, V0 square cutoff divided by RL, and here P0 maximum will be equal to V0 square maximum divided by RL. Same thing for the power formula, V squared by RL. So here RL will be the load resistance which is connected across the filter circuit where the output has measured. So the cutoff output cutoff voltage will be equal to, so RL will get cancelled and square will cancel each other, and taking the root, so 1 over root 2. So V0 cutoff is equal to V0 maximum divided by root 2. So V0 maximum is nearly or almost equal to input voltage. So the maximum output which is coming out will be maximum. So whenever the total input is comes at the output, that will be the maximum. V0 is equal to Vi divided by root 2 at the time where the frequency of the input source will be equal to cutoff frequency. So cutoff frequency is also defined as the frequency for which the cutoff voltage reduces 1 over root 2 times the input voltage. That is called as cutoff frequency. So we can derive an expression for cutoff frequency using the same circuit. Let us consider, let Vi and V0 will be the input and output voltage which is given into the filter circuit, and I0 will be the instantaneous current, or I will be the instantaneous current and I0 will be the peak value of input. Therefore, the input voltage can be represented. So in the previous classes we are discussed about the AC source containing resistor and capacitor. For that, the voltage across the resistor and capacitor, that will be Vi, will be equal to I0 times square root of R square plus 1 over omega square C square. So the output voltage will be equal to, same thing by using Ohm's law, resistance multiplied by current in this case. So here we are measuring the output voltage across the capacitor, so we have to take the capacitive reactance, that should be multiplied by the peak current. So Xc will be the capacitive reactance. So the value of Xc is equal to 1 over omega C, R itself is equal to 1 over 2 pi Fc. So output voltage will be equal to I0 divided by omega C. So next, so to calculate the voltage gain will be equal to the ratio of output voltage to the input voltage. So we have the expression for output voltage I naught divided by omega c, and expression for input voltage will be equal to I naught into square root of r square plus 1 over omega square. So I naught will get cancelled each other, and the voltage gain AV will be equal to 1 over root of r square omega square c square plus 1. So this will be get by taking LCM of this factor, and this omega square c square will taken outside and it will be cancelled with omega c. So at f is equal to fc, that means the frequency of input source will be equal to cutoff frequency. At the same time, the angular frequency will be equal to angular cutoff frequency. The output, then the voltage gain of the filter circuit will be equal to 1 divided by square root of r square omega c square into c square plus 1. So by the definition we have the V naught is equal to, that means at cutoff frequency output voltage will be equal to 1 over root 2 times the input voltage. So it can be represent, voltage gain will be equal to V naught by Vi, that will be equal to by taking this Vi into the denominator of the left hand side. So 1 over root 2 can be represented as root of 1 plus 1. So comparing these two, equation 1 and 2, so see this, so the left hand side 1 will be same, 1 divided by root, and this 1 is equal to r square plus omega c square into c square, that will be equal to 1. So keeping omega c whole square at left hand side and remaining things will be sent to right hand side, omega c whole square will be equal to 1 over rc. Omega c will be equal to 1 over rc. So omega is equal to 2 pi fc. So this is not omega c square, this is omega c. 2 pi fc into 1 divided by rc. Fc is equal to 1 divided by 2 pi rc. So cutoff frequency is the frequency which depends upon only the resistance and capacitance value. It doesn't depends upon the frequency of the input. Next, coming to high pass filter. So high pass filter is the same electronic filter. It consists, which allows higher frequencies by rejecting lower frequencies. It is called high pass filter. So it is constructed by using a series capacitor and a shunt resistor as shown in the figure. When the input voltage containing different frequencies are applied to the filter circuit, the capacitor offers high reactance to the low frequency signals and allows high frequency signals to pass through it. So in the output, we will measure the output across the resistor. Only high frequency components will be available at the output. High pass filter allows all the frequencies between the cutoff frequency and infinity, but it rejects the lower components of the frequency signals. So the frequency response curve for high pass filter is as shown in the diagram. For that we have to plot output voltage versus frequency. So the graph will be exponentially increasing. For lower frequencies the output will be 0 or nearly equal to 0, and as we increase the frequencies beyond the cutoff frequency, so the output voltage will reaches to maximum. That means in high pass filter, the capacitor or the filter circuit will allow the frequency components above the cutoff frequency up to infinite level. So in the same way as we discussed in the low pass filter, we can also derive an expression for cutoff frequency for high pass filter also. Let us consider, let Vi and V0 will be the input and output voltages, and I0 will be the peak value of current. So if we represent the input voltage in terms of current and resistance, Vi will be equal to I0 into Z, where Z is the impedance of the circuit, RC circuit. So impedance of the RC circuit we are already discussed in the earlier classes. So that is square root of R square plus 1 divided by omega square C square, and the output will be represented by V0 into I0 into R. So the voltage gain will be equal to V0 divided by Vi, which is equal to V0 is equal to I0 into Z divided by, and Vi is equal to I0 square root of R square plus omega square C square. So I0 will get cancelled each other, and the remaining thing is R divided by square root of R square plus 1 by omega square C square. At F is equal to Fc and omega is equal to omega C, the voltage gain of the high pass filter will be equal to R divided by square root of R square plus 1 over omega square C square. So taking R square outside the root, that will be equal to R. So remaining 1 plus omega square C square, dividing and multiplying by R square. We are already taken out R square outside. So remaining 1 plus 1 over omega square C square R square. So call this as equation number 1. By the definition of cutoff frequency, where output voltage is equal to 1 over root 2 times the input voltage, V0 divided by Vi is equal to 1 over root 2, that can be split into 1 plus 1. So call that as equation 2. So comparing equation 1 and 2, we'll get 1 over omega C whole square C square R square is equal to 1. So keeping omega C whole square at left hand side, remaining component must be sent to right hand side. Omega C taking root on both sides, omega C is equal to 1 over RC, omega is equal to 2 pi f, so 2 pi fc is equal to 1 over RC. So therefore Fc is equal to 1 divided by 2 pi into RC. So that will be the cutoff frequency of high pass filter. So let's discuss another filter, that is band pass filter. It is the filter that allows a certain band of frequencies to pass through it and rejects all other frequencies below and above the pass band. That is called as band pass filter. It will allows only a certain band of frequencies to pass through it and rejects all other frequencies below and above the pass band. That is called as band pass filter. The pass band is called as bandwidth of the filter. Whatever the frequencies it will allows, that range of frequencies is called as pass band of that band pass filter. The frequency response curve of the band pass filter is as shown in the diagram. So we can observe this if we plot a graph of output voltage versus cutoff frequencies along x-axis and output voltage along y-axis. We'll observe the graph like this. So from the graph we can observe two cutoff frequencies. One is lower cutoff frequency, that is represented by Fl, and higher cutoff frequency, that is represented by Fh. So the bandwidth will be equal to the difference between the higher cutoff frequency with lower cutoff frequency. That means BW, that is bandwidth, is equal to Fh minus Fl. So here we can construct the band pass filter by taking LCR resonance circuit. So we can construct band pass filter in two different ways. The first type is series resonant band pass filter and the second one is parallel resonant band pass filter. So first we'll discuss series resonant band pass filter. The circuit connections of series resonant band pass filter will be as shown in the figure. The L and C and R are connected in series. So here the LC has maximum impedance at resonance. Near the resonance, the current is passed by series LCR circuit that will be equal to maximum. The maximum voltage drop is produced across the resistor for the band of frequencies around the resonant frequency. So the bandwidth of band pass filter which depends upon the quality factor. So we have discussed this earlier itself. To have large bandwidth, the quality factor should be small because the bandwidth is inversely proportional with the quality factor. The relation between the quality factor, resonant frequency and bandwidth is Q is equal to FR divided by bandwidth. So again, the parallel resonant circuit, the circuit connections are made as shown in the figure. At resonance, here the LC parallel combinations offers maximum impedance and rejects the corresponding frequency of current. Hence, these frequency must pass through the load. Hence, these frequency must be passed through the load. So, the high frequencies are bypassed through the capacitor and the low frequencies are passed by the inductor. So, the bandwidth of band pass filter is again depends upon the quality factor. The quality factor, it is equal to the ratio of resonant frequency to the bandwidth. That is Q is equal to F naught divided by FH minus FL, or it is equal to bandwidth. So this completes the filter, single stage filter using RC filter as well as band pass filter. Thank you for the listening. Thank you.